How's it going? It's Brian. Now, I'm going to give you another technical demonstration of yet another tool that just popping up like, I don't know, like whatever, just pops out like weasels. It's a new tool called restruct. And again, as with ProtoBridge, I'd recommend copying this locally to your computer, which is where I'll be running it from. Now, what is restruct? Well, restruct is pretty much just, as the name might imply, a restructuring tool. More or less, its specialization is just reassigning tubing sections to your model, depending on whatever criteria you really feel like. Now, this criteria could be completely cost-based. And I'm just going to get this going, but so I can select which model. So you can basically resize tubings to optimize the overall cost of your bridge based on the typical scoring criteria, and you can define that scoring criteria basically here. So this pretty much accounts for all of the cases that you're going to be looking at in your model. Nominally there's only 6 cases, but I've actually doubled it because technically, in order to ensure symmetry of your bridge, or relative symmetry, you kind of need to also mirror your load cases across the bridge, because technically, if you're only looking at load cases applied to or from the right side of the bridge, then you're not going to be fully capturing the symmetry. So you have to double it. But that's okay, that's trivial. If you have ProtoBridge, you can automatically calculate and get a whole bunch of additional things. And then once you have all that and you've imported it into here, then you can pretty much specify all the points at which you're going to be measuring deflection for each particular case, and the load combinations that correspond to the starting point or starting step that you're going to be measuring load at, and then the difference between the starting step and the ending step loading, or rather deflection values at that particular point. Alright, so that's pretty cool. Now, what do you have, or what do you have that, or what do you do when you have this? And you've already specified what your deflection and your weight cost multipliers are in your model. So $1 million per inch and $20,000 per pound. Well, you can specify which groups in your SAP model you want to optimize, pretty much. And I'm just going to select something simple like legs, because optimizing through all of the sections, it takes a while. It takes about 10 minutes, I think I've found, to resize all of the frame sections. But, it's still pretty cool if you can do that. So that's an option. You can just kind of select all, select resize frame sections for cost, and it'll automatically resize all of your tubing sections in the model to their optimal values. But I'm just going to do legs for now, and I'm going to click resize frame sections for cost. And basically what this is going to do is it'll pretty much go through my model, get all of the numbers that are in the legs group, and that'll be a smaller subset of the total number of frames in our model. Now there's here about 487 total frames in the model. We're only going to be looping over a few of those, however many are in legs. I forget how many there are. But you can pretty much go through, and it'll give you this nice little progress of how far it's going, so you can kind of like time your bathroom breaks or something, or getting a cup of coffee. And once it's done, bam, it'll pop out and it'll show that it made 14 overall changes. So there were 14 frame sections that it made changes to, and it has a list of the old sections from the previous iteration and the newly assigned sections in this column here. So what does that look like in our model? Now, if you recall, originally in our model we had these legs all with the 1/2 inch 028 or 035, I forget, tubing diameter. But look at this, now these inner ones are actually a little bit smaller. They're 5/16, and this is pretty much taken from the full Wix tubing database. It'll automatically search through the available tubing sections and try to find the optimal one to use for that section, depending on how much load it's actually taking. So likewise, you can kind of just do it again pretty much, and I'll just kind of double click it again, And notice that this is indeed an iterative process in that if you just do it once, it won't necessarily get you to the global optimum. You have to kind of iterate through this. So just keep re-clicking it, and eventually, if you get to the point where the number of changes that you see in the model goes to 0, then that pretty much means you're done. You don't need to iterate anymore. But basically, if you want just like a really quick, dirty estimate of the optimized model, you can maybe do a single iteration, and that'll get you part of the way there. Now you can see it went from making 14 changes to now it's only made 9 changes in the model. And you can kind of see it's a little bit different. This is now something, it's 1/4 inch, so it's getting really small. Now this is probably where you're starting to say, hey, wait a minute, 1/4 inch by 0.28 thickness? Oh no, I definitely do not want that in my model. No, get out. So what is that? Well, how do we get around this? Well, basically, the optimal tubing size is not necessarily designed for strength. It's designed for cost. And that's precisely what the name implies. We're optimizing it for cost. We're resizing the frame sections for cost. But it doesn't make any mention of the strength of the member. So it can get this really thin if it's only taking a little bit of force. But even if this is in compression and it's only taking a little bit of force, that might be enough force to cause this member to buckle, which is bad. So how do we get around that? Well, the simple answer is to just use resize frame sections for strength. And this actually applies to all of the frame sections of the model, regardless of which groups you've selected. So if I click resize frame sections for strength, it'll run the model, and then it will automatically run the steel design checks in tandem. And it'll use that steel design check information in your spreadsheet. See, it's preparing to resize our sections, and then it'll automatically determine which ones are failing. Here there's 15 sections that are failing that it's determined are bad, and it's gone through and it's resized some of those failing tubing sections. But it hasn't resized them all too significantly. It's only made minor changes. So this currently has 15 sections that are failing. Let's check, see if I resize this. Maybe if I do it again, there will be fewer changes that it has to make. There will be fewer members that are failing. But let's double check. Look at the model, just a little bit. So again, as with the resizing for cost, resizing for strength is a similar matter. You kind of have to just iteratively keep pressing the button until the number of changes goes to 0. But you can see actually last time we had 15 members that were failing that we had to bump up a little bit. This time there were only 13 members that were failing, and I bet if I did it again there might be even fewer. But I don't know, I wouldn't stake my lunch on that or something. But yeah, so you can kind of do this whole process where I probably recommend resize all your frame sections until you're getting very few changes for cost first, so you get the fully optimized model for cost, and then once you've gotten to that optimum, just kind of go through resizing your frame sections for overall strength. Or I don't know, maybe you could even like swap between them or something. I don't know, whatever really suits your fancy for that. It doesn't really matter. Maybe you could do like one of these and then one of these, and then just kind of make sure that yeah, at each iteration those members aren't failing. So yeah, you can kind of play around with this just to get a good happy medium. Anyways, so hopefully this seems pretty cool to you. I think it's pretty awesome. And to give you some context, I said, if you were to optimize like all of the frame sections for cost, it'll take about 10 minutes to run or something like that. But that's chump change. I mean, compared to the amount of time that you're saving. These are by no means trivial calculations that are being done in this. This is like numerical integration over every single element, fully integrated. It's pretty expensive computationally, but it gets you there. It's much easier than having to whine and get a headache over the fact that you have to basically resize and try to iteratively resize every single tube in your model. That just would take forever. So 10 minutes, that's nothing. That's absolutely nothing. Alright, well, hopefully that was cool. I'll see you guys next time.